The first one is fractionalization, a basic phenomenon in many things in condensed matter. And the second one will be on non-Fermi liquids or metals without quasi-particles, also a topic of great interest in many modern quantum materials. Okay, so the idea of fractionalization really is quite old, and in some ways the earliest place where fractionalization made an appearance was the idea of the resonating valence bond wave function, which goes back all the way to Pauling, and then Anderson in particular focused attention on it and pointed out some of its remarkable properties. Today we know the correct way to characterize these states is in terms of all kinds of sophisticated measurements of topological order and entanglement, but I largely not go into any of those technical details. I focus instead on the basic idea of fractionalization. So what is fractionalization? So here's the basic resonating valence bond wave function. You have a bunch of spins on some lattice, a triangular lattice, for example, with a Hamiltonian like this. So on each side of the lattice, there's a spin operator that acts on a given set of states, which transform under some representation of SU2, S equals 1/2 is usually the case of interest. And there's some interactions between the spins. I've just put the nearest neighbor interactions, but you can imagine many more. So the idea is that a system like this could form a ground state, which is a character wave function, which looks like this. So the spins like to form singlets. For example, the J's are positive, the nearest neighbor J's are positive. So they like to form spin singlet states, shown here for spin 1/2 of these two spins. And each spin can only pair up with a single one. So there's some configuration of dimers, as they're often called. And this configuration I label by the label D. Now there's many different ways of pairing up the spins. If you want to do only nearest neighbors, these are close packed dimer configurations. And the RVB wave function is just a superposition of all these wave functions, so all these states. So it's a state that, at least on the infinite lattice, is non-degenerate. The most interesting cases have have a gap and no broken symmetry. But nevertheless, there's something long range about it because it's really a superposition over an infinite length scale of quantum things. There's entanglement, I guess the word we use today, which is in a precise sense long range. So, and it's taken many years to appreciate and understand all the subtle properties that a wave function like this has. So it's something really new in condensed matter physics anyway, when it was introduced, although it took a while, as I said, to realize it, and has properties that are quite different from the usual wave functions in condensed matter, like the BCS wave function or the Fermi liquid theory or some kind of antiferromagnet that you meet in a condensed matter course. Okay, so what are some of its, I'll focus on the property of fractionalization today. So what is fractionalization? Well, the point here is that any local operator that you can act on the Hilbert space always creates states which change the spin by plus or minus 1. So any local operator creates states with delta S, meaning the spin different from the ground state, which is integer, 0, plus minus 1, plus minus 2, and so on. So for example, if you act up like a spin operator on this side, that can convert the singlet to a triplet. And so the singlet will disappear and you get a triplet. So the spin of this object relative to the ground state, delta S is 1. So it's an integer spin excitation. And anything you observe in an experiment, any probe that you can put on this spin system, without actually removing an electron, which we are not going to allow in the definition of this Hamiltonian, always changes spin by an integer, even if the underlying spins have spin and half. However, fractionalization is the idea that if you have a liquid state like this, it's possible for these two spinor halves to move infinitely far apart. So that would involve some highly non-local rearrangement of these singlet bonds, and hence the emphasis on local operator. If you allow for a non-local rearrangement, what the system will do on its own, once you create this, then these singlets can rearrange. And the free spinor half could be over here. And everything else will repair itself, and you'll get some sea of singlets behind. And so this spinor half can move infinitely far away from that. And now you really have a local excitation here, which relative to the ground state in its environment has delta S equals 1/2. So this thing is the fractionalized excitation. Delta S here is plus or minus 1/2. So the spin is split into two objects which carry spin 1/2. And there's no such object in an antiferromagnet or ferromagnet. All the spin waves or magnons that you hear about all have delta S equals 1. So this is the postulate that this can happen. And then once you do this fractionalized excitation has all kinds of interesting properties. It can have non-trivial statistics when you exchange two of these. Hence, they can be anyons of different types. And often that's it's written in terms of a coupling to an emergent gauge field. So you need a gauge theory to describe the dynamics of these two objects. It can be a fermion, it can be a boson, it can be a semyon, and I'll hopefully mention various examples of those states. And really, that's kind of what we want to focus on, different examples of when this can happen. That's what I'll do in the first 2 lectures or so. Okay. All right. So in fact, what I'm going to do today is focus on an even simpler model. Since it's a course in statistical physics, I'll really talk about a classic model of statistical physics, which is actually purely classical. It's a stat mech of classical spins. And that can also exhibit fractionalization. I'll try to show how that happens. And that will teach us a lot of techniques that we can then apply probably next time on a more complicated quantum system like this one. So for most of today's lecture, I'll talk about an even simpler model. I'll talk about the classical XY model in dimension d equals 3. So, right, big D, I mean, that's the full dimension for a classical model. If I'm going to interpret this model as a quantum model, where one of the dimensions is time, which you can, then this is a quantum model in little d equals 2 dimensions. So it's a very basic model. Partition functions can be easily written down. D theta over 2 pi, where I sits on the sides of a cubic lattice, is x into, well, some on nearest neighbors, let's say, to begin with the coupling J here of cosine theta I minus theta j. So this is the basic XY model where I have a cubic lattice, and on each side of the cubic lattice, I have an angle, an XY variable theta, that goes between 0 and 2 pi. And there's a coupling between them, which is ferromagnetic, which I'll write as J. So when J becomes very large, all the spins line up and you get an X-like ferromagnet. And when J is small, which is the high temperature limit of the classical model, then you get some disordered phase. Okay, so this model as written is of course something that really nothing new can be said about. It's been thoroughly studied over many years at the basic work of statistical mechanics. And really all the interesting stuff that I'll focus on is what happens when you add further interactions and frustrate it in some interesting way. But let me quickly review what the properties of this model. So in D equals 3, it has a phase transition, which I've already alluded to, between the ordered phase and the disordered phase. So as a function of J, or inverse temperature, so let me make this 1 over J, which is sort of like temperature. There are basically two phases. This is the ferromagnetic phase, or the long-range ordered phase, where if I now define complex field psi, it's e to the I theta I, then the limit as r goes to infinity of psi star of r, psi of 0, is equal to some complex number psi 0 squared, which is not 0. And that's the long-range ordered phase. And then there's a high temperature phase, which I'm going to call, for my own reasons, the trivial phase. And what happens in the trivial phase, as this correlation function goes to infinity, as r goes to infinity, this decays exponentially with some correlation at c. Okay. So the existence of this phase transition, I guess, probably goes back to a different context, the van der Waals mean field theory in the 19th century. Then there was the Curie-Weiss mean field theory, which was applied to this for a 3-component spin. That's the Curie transition of a ferromagnet. And then ultimately, the theory of the critical point was given by Wilson and Fisher. It's a 3-dimensional conformal field theory, of which we know a great deal. Okay, so really not much more to say about this basic model, but I want to show you today that if you deform it, there's another possibility, and that possibility involves fractionalization. And that possibility is also present for the classical model, although in the classical model, to really see fractionalization is a little subtle. But if you interpret this model as a quantum model and look at its correlation functions in real time, not in imaginary time, then the distinction is extremely clear and very similar to this distinction I mentioned above. Okay, but let's just for now, just think about this as a classical model. And let me define what I mean by fractionalization in this model. So to do that, I have to look at this trivial phase in a bit more detail. So what we know is that the correlation function, not that it just decays exponentially, but also there's a power here, which is r. It's not just a pure exponential, it has a 1 over r prefactor. And this is sometimes called the Ornstein-Zernicke form. Okay. And this, this is nothing mysterious. You just get this by, I just take the Fourier transform of d3k over 8 pi q e to the I k dot r of k squared, that's c inverse squared. Just perform that Fourier transform and you'll get this 1 over r. So this is also then easy to measure in experiments. And also, it's been proven rigorously by mathematical physicists, Froelich and others, that this is rigorously true in the high temperature phase, this 1 over r prefactor. It's something you get right away from just the simple calculation, but it's also rigorously true. Okay. All right, so now let me just take, to introduce fractionalization, let me take a point of view where I think of this as a quantum model. So what kind of quantum model, what kind of phase transition would you describe in quantum mechanics? Well, it describes what we would call the superfluid insulator transition. So superfluid insulator transition, you take a bunch of bosons, not spins, but those are closely related, of course. But in the simplest case, you take them at integer filling. So you have bosons at integer filling. Let's say 1 on the square lattice. So there's some, typically you write it in terms of a Hubbard model. So there's some repulsion between the boson. U is the repulsion between the bosons, and T is the hopping of the bosons. And you put them on a square lattice. So when U is very small, you have a VEC or a superfluid. This is at T equals 0 now. And in 2 spatial dimensions. And this VEC obviously corresponds to the long-range ordered phase of this XY model. And at large U over T, you have a mod insulator. And in the mod insulator, the repulsion U is so large, and since you have 1 boson per site, the boson will just localize 1 on every site. And now you can see why I call this trivial, because this is a simple trivial product wave function, and that obviously corresponds to this. Now this particular state has a gap, and that gap is precisely the inverse of the correlation length. So this state has a gap, delta, which is equal to 1 over C. And what is it a gap to? What are the excitations? Well, the excitations are particles and holes. You could add an extra particle somewhere, and this will now move around. And that extra particle will cost you some energy because it's repelling a boson that was already there. But it can move around freely because it pays the same energy cost on every site. And similarly, you can have a hole. You remove a boson, and this hole can move around. And that also costs energy delta. So you have particles and holes. And it turns out this phase transition is exactly the Wilson-Fisher transition. It's particle-hole symmetric. They're both particle and hole excitations. So it's a relativistic quantum field theory, whereas here this was, just a field theory, 3 spatial dimensions with full rotational invariance. And they're exactly the same theory, and the universal properties of these transitions are exactly the same. And you can translate here things over there to things over here. So now this operator psi is now the boson created operator. And what does it create? Well, it creates or annihilates a boson of number 1. Okay, so here the excitations have boson number, which I'll call Q, which is plus or minus 1. So the integer excitation, just like the integer spin excitations of a trivial antiferrous magnet. All right. So the question we want to ask is, in some, if you had complete freedom to tune the Hamiltonian obtained by these bosons, could we find a phase of these bosons, just boson with local repulsive interactions, where the excitations has Q equals plus or minus a half? Would there be some sort of gap phase of that type? And I want to compute, so the answer is yes. But I should hasten to add that, although there are experiments of this superfluid insulator transition today, there are no experiments of that type yet of bosons at integer filling. It turns out that the more interesting case for quantum experiments is bosons of half integer filling, It's a bit more complicated, but I'll just treat this one for now theoretically. So the question one can ask is, can the psi boson fractionalize into two, let me call them phi bosons, with boson number Q equals plus or minus a half. Okay. And very qualitatively, you might say, well, psi fractionalizes into phi squared. Can this happen? Can I get a gap phase where psi has split into two? Okay. Well, let's suppose it does, and these phi then are perfectly good excitations. They move around almost like free particles. But every time you hit a psi, you add a boson or remove a boson in some experiment, it splits into two bosons. Can this happen? Well, if it did happen, how would we know? Well, in the quantum life, it's quite easy to tell that something is split into two. You do a dynamic neutron scattering experiment, and instead of getting a sharp peak, which is a quasi-particle resonance, you'll see a continuum of different, all the different two-particle states that we created. So it's quite easy to see how to see that here. But in the classical model, it's a bit more subtle. So imagine phi is now like a free field, not psi, and I'm in the fractionalized phase. So we can see that the gap to creating psi will be twice the gap to creating phi, because you get two of the phi's. Or in terms of the correlation length of the phi will be twice the correlation length of the psi. So the phi correlation function will go as e to the minus r over 2 psi over r. And if I just take the product, now I come up with a psi correlation function, which is e to the minus r over c, with r squared. Okay, so that's still a very sharp question. Could you, it's all here. Even in a purely classical model, if you're doing a stat mech of this very simple model with some additional interactions, could you get a phase, which is not the trivial phase, but we'll call it the fractionalized phase. And it's going to differ from the trivial phase by something very subtle, at least classically. The correlation function decay exponentially, but the prefactor will not be 1 over r, as it is for the usual XY model, but 1 over r squared. Could this happen? Yeah, all right, so that's what we, although the difference is subtle, this already tells you that this phase cannot be smoothly connected to this phase, that there must be a phase transition between the trivial phase and the fractionalized phase. So if I'm going to draw a phase diagram, let me go up here. Then I can imagine adding another phase here. Okay. Color here. So now I have another phase here, which I'll call in some, I want that. Now, what is this axis? I don't know yet. But this is the fractionalized phase. And here the excitations have Q equals plus or minus a half. Here Q is integer. And the correlation function, okay, I'm running out of space. Psi correlation go as e to the minus over c or r squared. All right, so what I want to talk about now is give you an example of a way of thinking about getting such a phase. And this leads to actually theories of all of these phase transitions, which are, this of course we know, but the other two are fairly novel. And what happens down here? Well, we still don't know, actually. It's still an interesting open problem. If you have such a fractionalized phase, what happens where all three phases meet, or do they even meet, or something else happens? Okay. All right, so that's the problem I've proposed to you. Let's just talk about the XY model. We're going to add some other interactions. So, what the kind of interaction I have in mind. So, for example, I could add interaction K, which is sum over squares of cosine of theta I plus theta J minus theta K minus theta L. And what's the rule here? Well, the rule is, first of all, you have to preserve, there's a global symmetry here. The global symmetry is you can shift theta by any constant, the same constant on all sides, and that shouldn't change the Hamiltonian. And the other is periodicity, that you can rotate any of the thetas by 2 pi times an integer, which can be different on different sites. Every term should preserve both of these features. Apart from that, I don't put any restrictions at any, and you don't want anything infinite range. The term should decay exponentially once the number of spins become large enough. But in this class of models, can you find, for example, a phase like this? And that would be the toy model, the simplest context in which you get fractionalization. All right, so I'm going to give you a proposed answer. It's not a proof. And the key to finding such phases, I mean, you could just put this on a computer and you find it's very hard. It doesn't immediately give you anything like this. Is to rewrite this Hamiltonian in a different way and use emergent gauge fields. So I'm going to rewrite this model using a different set of variables, which initially would seem a little crazy and cumbersome. But you'll eventually see that really I'm talking about the same model, and it leads to a much more natural way of getting a phase diagram like that. All right, any questions so far? Okay, you can all hear me clearly and at least understand the claim and the problem that I proposed. Okay, so I'm just pull out of my hat another model. And this is motivated by a lot of work on quantum spin systems of the type I began my lecture with over the years. But that won't be clear, at least today. And it's really the simplest context where I think I reduced everything down to the most basic ingredients in which fractionalization can happen. All right, so I'm going to make a change of variables. It's a redundant change of variables. I'm going to write the complex number psi as a product of two complex numbers, hi and phi I squared. So just going to make this identification. So psi I is of course e to the I theta I. And this is going to be, oh gosh, what did I call e to the hi in the notes? Oh, that's all right. I used curly theta here, curly theta I, and this is e to the 2i curly phi I. I'm sorry. Hopefully you can see the difference between the different angles here. Okay, so I just take my angle theta and write it as a sum of two other angles. Right? Theta I is equal to var theta I plus 2 var phi I, and of course this is mod 2 pi. All right, so the moment I do this, I reduce the redundancy. And that's, of course, the gauge invariance. So this is a U1 gauge invariance. So I can do a gauge transformation of these variables. I can change theta goes to var theta I plus alpha I, and bar phi I goes to bar phi I minus 2 alpha I. So alpha I can be anything, and this change of variables should not change any property of the original theory, which only involves psi. Okay, this is just a change of variables that I'm making. But what I'm going to do now, yes.
Sorry, isn't the 2 in the wrong place? It looks like it's theta that needs the 2.
Thank you. Yeah. So the field H, which I'm calling H because it's going to become a Higgs field, has charge 2 under this U1 gauge symmetry. So there's an explicit U1 gauge symmetry. And this field phi, well, that's going to become the fractionalized boson. It has charge 1 or minus 1 under the same U1 gauge symmetry. The field theta, the original XY field, is neutral. If theta doesn't know anything about the gauge symmetry, any operator that you can act on the system is gauge invariant. Only involves theta. So these other fields are figments of our imagination and are hard to detect directly. Okay. So having done this, I'm just going to write a partition function, which I'll call ZU1, which will be an integral over, the highly redundant integral now, over these other fields, the var theta I over 2 pi, and integral d var phi I over 2 pi of some Hamiltonian minus H, which will involve, theta variable and phi variable. Okay. The notes have these things written out much more clearly. I'm sorry, this is not the best. My penmanship or chalkmanship is not the best. All right, so we want to write down some Hamiltonian, and it must obey these rules. And it turns out the simplest way you can do this is by introducing a third variable, which I'll call a mu I. And this variable will sit on the links of the lattice. Okay, so I have 2 lattice points here. The H and the phi lives on the sides. And between each pair of sides, I have a field which also goes from 0 to 2 pi, which I call AI mu. And that's going to become, of course, the field of electrodynamics in a few minutes. Okay, the reason for introducing this is it enables us to write down Hamiltonians that have these simple symmetries. Otherwise, it's quite hard to find anything. In fact, if you didn't have the mu, you'd just be back to writing down Hamiltonian this type, where you just substitute theta to be this. Those are the only possible Hamiltonians that have this large symmetry, this gauge symmetry. Okay, but once you have a gauge field, you can write things down a little more explicitly and get a much larger class of systems. So the H here is going to be what? So now I'm going to deduce some notation, minus J1 of cosine of d mu of phi I plus AI mu minus J2 of cosine of d mu of the var theta minus 2AI mu. And then finally, K sum over plaquettes of cosine of, well, let me write it as del cross A. And I'll tell you what that del cross A is. So if you have a plaquette here, this del cross A, or the curl of A for every plaquette, is just equal to the sum of the A's around the loop, the oriented sum of the A's around the loop. And here, this A actually has an orientation. So if you go the other way, it's the negative. If you take the vector the other way, it has a negative sign. So if you take this oriented sum of del cross A and put a cosine, that's the last term. All right, now you can see that all of these three terms are invariant under this gauge transformation, provided AI mu transforms just like the usual gauge field, with delta mu alpha I. I hope I have the sign right. No, I don't. Okay. All right, so here, another important notation is that delta mu is a discrete derivative. That just means the difference of alpha I at site I plus mu and I. So it's just like the usual derivative, but you just take it discretely on the lattice. All right, so here's a theory that I pulled out of my hat. And the only, the guiding principle was this theory obey this symmetry right here. And also the global U1 symmetry and these symmetries. All of this is all obeyed by this particular Hamiltonian. And so now this seems to be nothing related to this. But now I invite you to just do the integral over mu. And you can just do the integral by expanding powers of k. This k is up in the exponential, and assume k is small. And you do the expansion in powers of k, and do the integral over a mu on every link. It'll basically be the integral of exponentials of some cosines of a mu. So that gives you various complicated Bessel functions. And then you re-exponentiate them and do a Fourier series expansion. You're guaranteed to end up with something like this. Eventually, actually, one of the exercises, you will do an integral like this in a simpler theory. This is a bit messy, but I hope you can see that this theory is just one instance of this kind of theory with many more terms, all short-ranged, at least in the expansion region where the expansion in K is possible. Okay. So this is just still the XY model, but written in a new set of variables, which are designed to eventually give us fractionalization. Okay. All right, any questions on the notation or what I've written up here?
I have one question.
Yes, please go ahead.
I lost the definition of I mu.
Which one?
The gauge field, the last gauge field introduced.
So it's just a variable that sits on every link. And the variable has an orientation and goes between 0 and 2 pi. So every link of the lattice has a degree of freedom, which goes between 0 and 2 pi. And I just use a notation that AI mu is the negative of AI plus mu minus mu. So if you go, this is the site I, this is the site I plus mu. So this orientation is AI mu. And if you go the other way, that gives you a minus I. Okay, so it's just a vector, a periodic variable that goes between 0 and 2 pi. And this term, if I expand out the cosine to second order, that's just the Maxwell term, discrete version of Maxwell electrodynamics. But here it's what we call compact electrodynamics because of the cosine, because of the periodicity. A goes from 0 to 2 pi, it doesn't go from 0 to infinity. That's actually quite important. That you wouldn't get the XY model, you get long range interactions if you didn't have the cosine. The integrals won't be defined because you have the cosine. All these integrals are perfectly well defined, and you expand in powers of k. And you just get finite numbers at each order, and you get terms of this type, and they're multiples. You get cosine of 2 theta I minus 2 theta j, and all of that. Those are also allowed. Fractions are not allowed, but any multiples are allowed, because as long as they have these symmetries. And when you do the integrals, you're guaranteed to only get results that depend on this combination. Because that's the only way they could be gauge invariant, when you don't have a gauge field.
So this, regardless of the values of J1 and J2, they don't need, there is no constraint on the two values with respect to the original J in the original model.
So there is some constraint. You can do the expansion in powers of k, and you'll get some, maybe I should call this k tilde here. You do the expansion powers of k, And you will get some expressions for this J in terms of this J1 and J2 and the K. Will depend on that. They're complicated expressions and many more terms, but they'll all be short range terms which don't go out to infinity and they decay exponentially. Those are complicated expressions. I'm going to skip it. The notes give you a little bit more, a few more steps on how to do that. We'll eventually look at an even simpler problem where you can actually do this much more easily. And in fact, that will be a homework problem. So there is some relation between J and K tilde and J1 and J2 and K. I'm just leaving it, not going to derive it.
Okay, thanks.
And another question, do the dimension is playing a role at equal 2 equal 3 in this rewriting?
I can certainly write it this way in any dimension. But the claim that this kind of model will give you a phase diagram like this is special to 3 dimensions. It does not happen in 2 or 4, things are different. But I can certainly rewrite this model in this form in any dimension. It's just the dynamics of this model is quite different depending on which dimension you're in. So, you know, I have a compact U1 gauge field, and I have 2 fields, 2 charged scalars, the scalar H, which has charge 2, and the scalar phi, which is charge -1. And they can only make one gauge neutral combination, H phi squared, and that's the original XY model.
Could I ask a question?
Yes.
So the way we've written this, we've introduced a U1 gauge redundancy.
Yeah.
But if we imagine doing this some other way that adds in, you know, a different gauge field like SU2, for example, would we still get the same physics at the end of the day, or would that just be like expanding around an entirely different saddle point?
That would open up even more complicated physics. So this fractionalized phase I'm trying to talk about is a very simplest fractionalization phase, where psi splits into two objects which have the same properties. Psi is phi squared. There's no limit to the things that can happen. It could split into 10, and you can get all kinds of complicated gauge charges. Yeah, so this is just the simplest. That's all. And it's the most common, it's the one that really is most likely found in a lot of kinds of numerics and in some recent experiments in different systems. Okay. I'm going to simplify this further, as you'll see, where I'm going to reduce this gauge symmetry down from U1 to Z2. But I'm just going to work with U1 because that's really what appears in actual treatments of spin models, and also because you know, you're likely more familiar with U1 because that's the same symmetry as in electromagnetism. So I'm just doing Maxwell theory with a few twists. Okay, so this is the model we'd like to solve. Okay, that's not easy at all. So we'll just do what we always do, at least in condensed matter. You do the simplest possible thing. You do a mean field theory, and then you do fluctuations about the mean field. And that's, you know, what was very successful in understanding these two phases, starting with the Curie-Weiss mean field theory, and then, of course, eventually that developed into the Wilson-Fisher theory of everything, including the critical point. So let's try to follow that well-trodden path. So in mean field theory, you just assume you have some order parameter, and you write down some polynomial free energy for that order parameter. Here, the only complication which is important, is that we have two order parameters, if you wish, the h and the phi, in this, at least in this formulation, and they carry an additional U1 gauge symmetry, in addition to the global U1 symmetry, which you can put either on the h or the phi, depending on your taste. It doesn't matter in the end. But those are two very different symmetries, okay? So keep that in mind. This is the U1, oh, sorry, I erased it. This is the U1 gauge symmetry. And then there's another symmetry, which is the full theta going to theta plus C, which is independent of I. That's the global U1 symmetry. Those are completely different symmetries. And the fractionalization we're talking about is with respect to the global U1 symmetry. And you get global U1 charges which are half. Okay. All right, so let's just do a mean field theory. So we just write down some mean field free energies for the H and the phi. I want to follow the same notation in the notes. Okay. So we'll write down, we'll even take the continuum limit. The signs may be a bit off, but I'm just going to follow what's in my notes. D mu H1 squared. So this is like a Landau theory at H squared plus U1 H to the fourth. And then you have D mu minus I mu phi squared plus S2 phi squared plus U2 phi to the fourth. They can even be phi squared, H squared term, but I'll just, well, okay, I put it here so might as well. V H squared phi squared plus K epsilon mu mu lambda B mu A lambda whole squared. So that's just the naive continuum limit of this. And I'm not going to go into this, but it's important for some of the conclusions. It won't be, but in today's treatment, I won't really go into these details. You also have to allow for some monopoles because of the compactness of the gauge field, and you're putting it on a lattice. There are also like Dirac monopole-like configurations, the defects in the gauge field, where you have flux 2 pi coming out of a singular point, like a hedgehog. And that's important for some things. I'll refer to it briefly, but I won't really need it for my main conclusions on the nature of the fractionalized phase. So we can talk about this later if you're interested. Okay, so but let's just do the most naive thing. Here I have some free energy for compact electrodynamics coupled to 2 charged scalars with charges +2 and -1. Okay, so the very simplest mean field theory, let's put V equals 0 and just do mean field theory in S1 and S2 and just ignore the gauge field. Okay, then you're going to get 4 phases as a function of these mass parameters, S1 and S2. See, this is going to be S2, and this is going to be S1. And I'm going to call these phases A, B, C, and D. And very naively, these are just determined by what's condensed. So in phase A, both S1 and S2 are positive. So phi is not condensed, is disordered. H is equal to 0. When S2 is negative, phi is condensed. H is equal to 0. And here both are condensed. And here the Higgs field is condensed, where phi is not condensed. Okay. All right, so we've seen to, at least in mean field theory, gotten 4 phases, which is 1 more than we bargained for. We wanted 3. We went from 2 to 4, which seems like a bit much, or maybe that's what happens. And so now we have to really think about the effects of fluctuations of these 4 phases and ask how do these 4 phases map onto the original XY model, the gauge invariant degrees of freedom that I started with. All right, any questions on how I wrote this down? This is really just simplest Landau theory. When something's mass is negative, it condenses, that's all. Oh. All right, so let's go through these phases and try to see what's going on. So first, let's do this one here, where both the phi field and the H field are not condensed. So there, imagine S1 and S2 have gone to infinity. And so I can forget about the phi and the H, which is very heavy particles. And all I'm left with then is this term. So I'm just left with electrodynamics of a photon. And if that's all I had, I would conclude that this is a phase which has a photon excitation. And that would imply that there's power law correlations of even gauge invariant observables, like flux correlations with decay of the power law. And there were never such phases in the original XY model. In fact, I went to 4 dimension, this kind of what's called a Coulomb phase, the power law correlation does exist. But in 3 dimensions, it doesn't exist. And the reason it doesn't exist is because of this monopole term. So again, this is not something I want to go into right now. So, and there's a lot of treatments of it in the literature. So let me just say what happens here is, I call it Polyakov confinement. Because of the monopoles, the photon disappears and you have a confinement phenomenon very similar to that in QCD. These monopoles derive confinement of the charged particles. So basically the only particles left over are the gauge neutral particles, which are the psi particles. So in fact, you know, each particle will confine to form a proton-like object with 2 phi's, and this object will be confined. And so you'll have this exponential decay and only integer charge excitations. All right, so I'm not showing that, and this is the one thing I'm going to ask you to take on my word at this point. So the conclusion is that at least this phase A in the end is the same as the trivial phase of the XY model. Okay, so this is trivial. Hopefully by the end of this lecture, it's almost time for a break. We will rewrite things in a way that we won't even have to appeal to Polyakov confinement. As we'll see, the U1 gauge field, you know, it's basically disappears from the problem in all the phases. So eventually we'll get rid of it. Okay. All right. So maybe I'll say something about phase B, and then we'll talk about the others after the break. So what about phase B? Well, what is the feature of phase B? Well, phase B, phi is condensed. Okay. So let's just take, let's do the obvious thing. Let's take S2 to minus infinity. So the condensate of phi is very rigid. Okay, so phi is condensed. We can always choose a gauge. So in this field, choose a gauge where phi is equal to phi naught, which is some constant. And it's a large constant. Okay, so now the gauge symmetry is gone. And the photon acquires a mass, because this term here, if I just replace this by phi naught, this becomes a mu squared phi naught squared. That's the Higgs mechanism. The photon acquires a mass because of the Higgs mechanism. I can just fix the gauge. The gauge field is just completely out of the problem. And I just conclude here that psi is just H. And H is some massive field that's fluctuating. Phi is completely rigid. And H, psi is just H. And therefore, phi is gone, the gauge fields are gone, and H therefore has global charge 1. So this is also a trivial phase. So this Higgs phase is also trivial. And this line is therefore not a phase transition. It's just some crossover. So what we see here is an example of actually a very important phenomenon in particle physics. sometimes called Higgs confinement continuity. These two fields are not different. The Higgs phase, where as long as the Higgs field here is phi, not h. The Higgs field phi has a unit charge under the global U1 symmetry, so it has a fundamental charge. This is very similar to the Weinberg-Salam model also, where the Higgs field has the fundamental charge of the SU2 gauge field. So when it condenses, you get a state that looks pretty much the same as a confining phase. So the Weinberg-Salam model also has a confining phase at strong coupling. That's not where we are in the real world, but that phase would be indistinguishable, at least. It should be connected to the phase of our universe by a smooth continuity. And there's a similar thing here. Another thing you might say, well, in this phase, there are vortices. So I'll come to that after the break. That's really the crucial thing here. Think about the vortices. Well, the vortices of phi have flux 2 pi. And flux 2 pi is the same as flux nothing because the periodicity in 2 pi of the gauge field. And therefore, the vortices are nothing. They're really not physical objects. They're just artifacts of our gauge-dependent formulation. So there is really in the end no distinction between these two phases, and that's really like the high temperature phase of the XY model. Okay, I think it's time for a break, and then we'll talk about the remaining two phases. I guess I can let the cat out of the bag. This is, of course, the long and ordered phase, and this is the interesting phase that the rest of the discussion will be about. This is where you have fractionalization, where the Higgs field that condenses with H, and it has charge 2, not charge 1. Okay.
Can I ask a question?
Yes.
In principle, we can also add the terms like H phi squared plus complex conjugation, and then does it change the phase diagram?
Yeah, sure, but it won't change the main conclusions that I'm asserting. What kind of term you have in mind? You want H phi squared mod squared?
No. H phi squared plus complex conjugate.
Yeah, so that's what this is, right?
I mean plus because H phi squared itself is gauge invariant, right?
But it's not invariant to the global U1 symmetry.
Okay.
You have to have invariant both on the gauge symmetry and the global U1 symmetry.
I see.
Yeah, you can add a cubic term. It's a 6th order term.
Can I ask a question?
Yeah, sure.
So how the passing to the continuum is achieved, or the Landau-Ginzburg action is simply assumed to somehow hold in the continuum, or how the passing from the lattice gauge to?
Yeah, I mean, I just do the way you do it for the usual XY model. You do it by some Hubbard-Stanovich field, and then you integrate out theta to the conjugate variable, do some expansion. So everything, you can, any StatMech book, you can see how you go from the Ising model to the Landau theory. You do exactly the same thing for the first two terms, for H and phi. And then you just expand out this gives you directiveness. Yeah, the main subtlety is the monopole, which I didn't talk about. Yeah, so the monopoles here are the analog of the vortices in the 2D XY model. And the 2D XY model, you have vortices in your costless Thouless condition. Here, in this gauge theory in 3 dimensions, the monopoles are defects in the gauge field. And they have an action very similar to the action of vortices in the 2D XY model. So you get a Coulomb gas of monopoles. The Coulomb gas of monopoles is always in the plasma phase, in contrast to the Coulomb gas of vortices that Cosplay-Thouless showed had a phase transition. This plasma phase of monopoles implies this confinement of electric charges. Okay, so that's a very interesting story that I won't go into here, but Polikov's book has a very nice discussion of it.
So another question is, I think there's a Higgs confinement duality is what the Fractionalization first got, but does it apply to all compact gauge series?
Yes, as long as
to matter.
Higgs field has a fundamental charge. Yeah. In this case, the field phi has a fundamental charge, which the Higgs phi is the one that's condensed here. But when you go this way and H is the one that's condensed, then there's a phase transition. So we're going to come to that. Yeah, I mean, you mentioned Fredkin and Shankar. There is also a very nice discussion in their paper of something very similar, but not quite. This, they didn't have a global symmetry. They were talking about a gauge theory without a global symmetry.
So this Higgs and the confinement is actually comes from a different assumption from in their paper.
No, so this part of the phase diagram, so they basically only have phases A and D. They don't have B and C. I haven't talked about D yet. D is, of course, the most interesting phase.
And also, how can I reconcile the fact that the scalar condensed with the Elytral theorem? Because on a lattice, there's no non-gauge invariant order parameter, right?
Yeah, well, I mean, it's just a convenient way of talking about it. If you don't like the word condensed, I won't use it. I would say that, in the end, I'm integrating over the full gauge field. That's where the monopoles come in. And this phi is not a physically observable quantity. It's just a saddle point that I choose to do the expansion about. But that's just terminology. I think it's very convenient terminology. It's the terminology Weinberg uses to talk about the Weinberg-Salam model. And you could equally ask the same question of him. Why you're breaking gauge symmetry? Because Alice's theorem forbids it. Well, turns out we can do it. It's a good starting point, and you restore gauge invariance by properly thinking about fluctuations about it.
So in principle, there should be some gauge fixing when writing this down, right?
Yeah, I mean, you if you want to, yeah. So in this phase, yeah, it's convenient to just fix the gauge so that you don't have to worry about it anymore. But in other, sometimes you do have to worry about it, and yeah. So it's not, it takes some careful thought, but over here it's perfectly fine. As you'll see over here, it's a little more subtle. You can't just fix the gauge because of this factor of 2. And so there is still some residual gauge invariance you do have to worry about.
Thank you.
Okay, shall I start? I think so, yeah, 10 minutes past the
okay, great. All right, so we want to talk now about phases. The bottom phases, the C and D. So just to remind you, we're just talking about a very familiar XY model in perhaps unfamiliar degrees of freedom. And so far, we've only succeeded in getting phases that just the high temperature phase of the XY model. You've got those phases in really very complicated ways through some very subtle arguments. We just conclude that phases A and B are just like the high temperature phase of the XY model. So it seems like a lot of work for not much payoff. Okay. So now we're going to talk about the bottom two phases where we're going to get something interesting. And for both of these phases, we want to really also understand a little bit about topology. This topology, in addition to just the phi and h, this kind of theory also has some topological saddle points. And these are just the Abrikosov vortices that you learn about in superconductivity or Nielsen-Ninomea vortices. So what are the vortices here? So you can take either a vortex in H, you would take a vortex in H in phase D, or a vortex in phi in phase B. So you have a vortex where there's some singularity at the center, and there's some winding of the phase. So in phase B, phi goes from, has some phase over here and goes around, and when it comes back, it's an e to the 2i pi. So it winds by 2 pi. Okay, so this means that the phase of phi winds around by 2 pi as you go around. And so if you take the line integral dl dot d mu log phi I, the phase of phi, that's equal to 2 pi. And what Abrikosov has taught us, that you can actually have this phase winding can have zero energy, provided there's a flux. So in this case, the gate, the first derivative matches the other one. So this matches A dot dl, then this costs zero energy. So this tells us if you have a vortex in phi, it must have flux 2 pi, and then this configuration has a finite amount of energy. So it's a line in space-time, and a line in space-time with a finite energy is what we call a particle. So this theory, in principle, has a new particle, a topological particle that's emerged in the quantum language, which has finite energy because of this matching condition. So the gradient doesn't cost anything far away. Okay. However, flux 2 pi, as already mentioned, is nothing. And you can't, it's not detectable because everything is periodic in 2 pi. So this is completely fake. And this is why the trivial phase is the trivial phase. Phase B is trivial. There's no vortex-like excitation in the high temperature phase of the XY model, and neither is there one here. Okay. However, let's go to phase D. Phase D has the H condensate, doesn't have a phi condensate. And H can wind by 2 pi, H is single value. But now there's a factor of 2 and a minus sign. So this must be minus 2. Okay. So what we conclude is we have now a non-trivial excitation where A dot dl is plus or minus pi. And in fact, it doesn't matter, it's plus or minus pi because 2 pi is trivial. So there's the oddness and the evenness is all that matters. So there's a pi flux particle, which emerges in principle in this phase. So if I take S1 all the way to minus infinity, then I have a particle, a new particle in my spectrum, which has pi flux. So this is sometimes called the M particle if you're dealing with the toric code, or the Wison if you're for condensed matter. And it's not something we ordered. It's something that just emerges from the structure of the theory. So there's a new particle, and this gives us now hope that in fact this phase D is something very interesting. It's in fact the fractionalized phase. Now correlations of psi will still decay exponentially because psi is a product of H and phi. In fact, H we can, so H we can put equal to a constant. We can do that except around these excitations where I can't put H to a constant. There are these finite energy excitations which are there in the spectrum. But apart from that, I can put H equals a constant. And so I also have psi is equal to phi squared. So I've achieved my goal. So this is in phase D. I have a H goes to a constant apart from Y zones. And I have this phi particle. Phi is free and gapped. My psi, the physical observable, is phi squared, because H is a constant. So I've achieved what I wanted. And this phi particle is sometimes called the E particle if you're dealing with a toric chord, or the spin-on if you're dealing with spin systems. And it's the particle we wanted. It had a charge Q, which is plus or minus a half. And that's simply because psi is phi squared. So in terms of the global symmetry, it carries charge 1/2. So I have this really interesting new phase now, the fractionalized phase that I wanted, which in fact has exactly the same structure as the toric chord. It has an M particle and an epsilon particle. The M particle is this vortex that becomes a vortex of flux pi in the H field. And the E particle is the phi field. The difference from the toric chord is that these particles have a mass and their dispersion. The toric chord, they don't have either of those quantities. And also there's a global symmetry that the toric chord doesn't have. And the global symmetry is very convenient to choose the global symmetry to act on the phi. And if you choose it to act on the phi, then phi has a fractionalized charge. Okay. And what else? Well, another thing we can now see is that phi has a unit charge under this gauge field. So if I have an M particle here, and I take a phi particle around it, or let me call it the E particle, because I have flux pi, it's going to come out, if it starts out some wave function E, it's going to pick up a Berry phase, so it'll change sign and be minus E when it comes around, because it has unit charge and it's an Aharonov-Bohm flux, which is exactly pi. So this is sometimes called that E and M are mutual semionts, which is exactly, again, what's present in the toric chord. Finally, what we also learned is that you could imagine that, so now I have these two particles, and they have some interaction between them, which is short-ranged because the photon is gone, it's Higgsed out by the H field. And the interaction could be that they form a bound state. So that's another remarkable property of this phase that we didn't order. We just wanted to get a phase which didn't break any symmetry and which had half charges. And what we got, in addition to the half charges, was this M particle. And in principle, there's another particle that we have that could exist in the spectrum as a bound state. It need not, but as you could imagine, certainly acting on the system as operators to create such particles. There won't be local operators. But if you happen to have a bound state of an E and an M, this is what's called an epsilon particle. And I'll leave it to you to figure out the Aharonov-Bohm flux. This particle is a fermion. So we have this remarkable structure. We just took the simplest XY model, a classical XY model could have in its spectrum a fermion if you had sufficiently complicated interaction. And that's the bound state of the E and the M. Okay, and then now complicated fusion rules and lots of, now you open up books on category theory which try to classify such things. And this is really the simplest example of a phase that has fractionalization and topological order and long range entanglement, and which preserves time universal symmetry. Okay. So that was all really quick, but we did all the preparation to see this remarkable phase here, which can exist both in the quantum model at integer filling of bosons, and also in the classical XY model of all things. it can have a phase in principle which has the same structure as the toric code. And is described by a non-trivial topological quantum field theory here, which I'm not going to go into. Finally, there's phase C, and this is now, with all the things we've learned, it's relatively easy to see. This is nothing but the long-range ordered phase. Everything is condensed. The only vortices are vortices that carry energy that's logarithmically divergent, just like in the original XY model, the system size. So there's true long-range order. Okay. All right, so that was very quick, but immediate payoff. We've got a topological fractionalized phase. Any question?
Yes, I have a question.
Yes.
Can you explain again, please, why the charge of the A particle is like 1/2? I didn't get this.
Yeah, so suppose I just have one E particle far away from an M particle. Then in that regime, I can put H equals constant. And so that excitation with just one E particle, I know that psi is phi squared, and therefore then the global charge of psi is twice the global charge of phi. Okay, it's not mod phi squared, it's phi squared. And so it has charge 1/2. That's one way to see it.
All right. Thank you.
It goes back to exactly how I take the ultimate decomposition is like this. So under gauge symmetry, it's completely obvious. H and phi have gauge charges. Now the global symmetry of psi, I can put it either on H or on phi. There's some arbitrariness there where I put the global charge of psi. And depending on which phase you're in, different choices are appropriate. So over here, it's better to put the global charge on H. Over here, it's better to put the global charge on phi. And the reason you want to do this is you want the condensate, whatever is condensed, to not have a global charge. Because you put a global charge on the condensate, you're making life difficult for yourself. To define your global charge so that the condensate is neutral. And then it's easy to count global charge. You're always counting charge with respect to the ground state. And so you want whatever is in the ground state to be neutral. So if H is condensed, you want it to be neutral under global. If phi is condensed, you want to be neutral under global.
Another question. I did not get if there is some evidence why we should expect a bound state between the E particle and M particle, or if this was just a possibility you were considering.
It's a possibility. It's a possibility. I think, yeah, to get an abs, there's no guarantee that a given phase like this will have an epsilon particle in the spectrum. It just depends upon the details. But when people talk about topological phases, they're really thinking in terms of super selection sectors. That is, can you get a region of space which has exactly one E and one epsilon particle, and what would happen if it took things around it really, really far away, without them being actually a particle, but just some region, a sector here, which we call the epsilon sector. There's some big region of the sample that has both an E and an M. But that would be called an epsilon super selection sector. And that's kind of always has to exist. Whether there's an actual epsilon particle in some experiment is a wholly different question.
Could you tell us what's happened with numerical experiments of the XY model to try to find this phase?
There are none actually. We tried and we couldn't in the original XY model. Certainly, you can take this gauge theory arrow down, and I will actually show you some numerical results for a more complicated gauge theory. But well, yeah, for the half-filling case. But I'm not aware of any numerical studies of a pure XY model where all four phases have been seen, all three phases have been seen. Yeah, I think for the gauge theory, the arguments are pretty robust. I don't know if anyone's taken the trouble to do it. I just presented this model for pedagogical reasons, I think. As you'll see, the interesting case is a more quantum model, which I hope to talk about a bit before the end of today's lecture, where you go to half integer spins or bosons at half filling. Then the XY model has a topological term, a very phase term, which is not classical, it's quantum. And then, in fact, the possibility of a fractionized phase actually become more likely. And there is a lot of evidence of that. Actually, come to think of it, there is a paper by, even for integer filling, by Matronik and Sentel, who looked at a model of short bosons with short range interaction. It's essentially like the theory that I've talked about, where there is evidence for these three phases. Yeah, sorry, I forgot about that. I can send you the reference later. It's Matronik and Sentel in the early 2000s.
Thanks.
Search. Yeah. Okay, so now I'm actually now going to simplify things a little bit, which, you know, at least it doesn't allow us to use mean field theories as much, but it makes a connection to other models that we also know a lot about. In particular, it will eventually make a connection to Wagner's Z2 gauge theory. So what we're going to do now, and the simplification is that, you know, we want to build into the theory, the fact that these two phases are the same. You know, we went through all this trouble to create a photon, a U1 gauge theory, which has a photon. And at the end of the day, we found a theory where there's no photon anywhere. It's either confined or it's Higgs everywhere. So it's just gone. There's no free photon, there's no Coulomb phase. There could be a Coulomb phase, but not in 2+1 dimensions. In 3+1, there could be another phase. But in 2+1, since there's no Coulomb phase, let's try to get rid of the photon completely. Okay, and the simplest way to do that is to go back to the original lattice model and write things in a certain limit. So what we're going to do, so the original lattice model had a term which was minus J2 of cosine of d mu r theta I plus 2 AI AI mu with some J2 in front of it. Okay, so let's just take the limit J2 goes to infinity. I mean, this is just some limit we want to study the model. It may be that if we take the limit, we lose some of the interesting physics, but as you'll see, we don't. Okay, if I take this limit J2 goes to infinity, then I can also work in the gauge where theta is just a constant. And so I get a cosine of 2a mu, so a very deep minimum. And so I might guess that I'm going to now restrict myself to the minimum of these. So I'll take my AI mu will become a discrete variable. It's going to be 0 or pi, because that's when this action has the least action configuration. So I take the U1 gauge field, which has a continuous variable from 0 to 2 pi, and reduce to a discrete variable, either 0 or pi. And so now on each link of the lattice, I have a discrete variable, sigma ij, which is equal to plus or minus 1, which is the same as e to the I AI mu. So sigma I plus mu. So I've almost got rid of the gauge field, but not quite. I've replaced the U1 gauge field by a Z2 gauge field. It seems, you know, kind of intuitive. What we have to keep track of here is these factors of 2, whether you charge a half or 1. That's really all that matters. The photon doesn't matter. So let's just see what happens in this limit where I replace A mu by a discrete set of variables. Okay. So what about the original theory? This becomes a much simpler theory because the J2 term is gone, and I only have the other two terms left over. So I'll write it down. Okay. Z. Now this will be a Z2 gauge theory. it will be integral over the phase of phi, d var phi I over 2 pi, and sum on sigma ij on each link of the lattice. I have a discrete Ising variable, which is plus or minus 1 of some Hamiltonian. And what is my Hamiltonian? Well, H is minus, I have the J1 term, which was cosine of phi I minus phi j. And it has a single charge, and if you just work it out, that just gives you sigma ij here. And then the k term is just the product, sum of k times sum over plaquette of product of ij belonging to a plaquette of sigma ij. And that's it. Okay, so now I have a Z2 gauge theory of a matter field, which is phi. So my physical observable psi, psi is phi squared, and yeah, it's easier to think in terms of psi is just phi squared, exactly that, and of course phi I e to the I var phi I, which is what appears here, and sigma ij is the variable on the links of the lattice. So here's a sigma ij on each link, and now you just take the product of sigma ij around the loops of the lattice. And now phi I is again an unobservable quantity because it has a Z2 gauge charge. So now I have a Z2 gauge invariance. Where sigma ij goes to eta I, sigma ij, eta j, and phi I goes to eta I, phi I, and eta I is plus or minus 1. So I can, I have a discrete Ising variable on each side of the lattice. If I flip it, then it flips, if I flip eta on this side, it'll flip the signs of sigma on all 4 bonds, or all 6 bonds connected to it in 3 dimensions. And it'll also flip the sign of phi, but it won't change this value because that's the product of sigma around the loop. And that won't change because only an even number of signs have been flipped on every loop. Okay, so this term is what's called the Z2 gauge theory in 3 dimensions, originally studied by Wegener. And all we've done is just added a macro field coupled to the Z2 gauge theory. Okay. And now you can see if you can actually, it's an interesting homework problem. You just take this partition function and you expand in powers of k. You expand this whole thing in powers of k, and you do the sums over sigma I. So you only get a non-zero contribution if you have 2 of these sigma ij in the expansion. Otherwise, just cancel out to 0. And you'll get some expression which involves only the phi I. And now it's actually quite easy to see explicitly that that's just an XY model in terms of 2 phi I. So this model here, so an expansion in K, and you sum over sigma ij, which is easy to do in this expansion, you get an XY model in the field which is 2 phi I, which is the same as theta I. Okay, so we've done exactly what we set out to do. We split psi into 2 fields. Psi goes to phi squared. And the only way to consistently do that is to write it in terms of a Z2 gauge theory with this term here. Every time phi hops from side to side, it picks up a factor of sigma ij. Okay. And so this theory has exactly the 3 phases there. And this certainly, I think, I'm sure somebody simulated it, something like this, and you'll get those three phases. I have a sketch of it right over here. Yeah, okay. So now if you look at the phase diagram of this theory, it'll be interesting to compare with that. I hope we have the same. Now the axes are J1, I think, or I call it J1. Okay, this is just very schematic. You get phases like this. This is the LRO phase. This is like phase C. And then here you have the confining phase. Phi is 0. Phi is condensed. And down here, phi is 0. And this is the fractionalized phase. So here, I unfortunately can't just do some Landau theory. This Ising-Gates theory is a bit more complicated than that. But you can try to understand things a little bit. So when J1 is very small, then phi is fluctuating a lot. So you forget about it. And you end up with a pure Ising-Gates theory. So this theory is what Wegener studied. And we'll talk about it next lecture using a quantum language, using strong and weak coupling decomposition. Not next one, but this one after that. And it's dual to the 3D Ising model by a Kramers-Wonge duality. And that transition of the dual Ising model, Wegener show corresponds to a confinement, deconfinement transition of this theory. So over here, when K is very small, when sigma fluctuates a lot, then the Z2 charges are confined, as Wegener showed. And out here, the Z2 charges are free, and that's, of course, the fractionalized phase at large K, where sigma ij is just frozen to 1 when K is very large, and therefore the phi particles become the E particles. And it's also easy to see what is the Wison here. Well, the Wison is just a configuration like this. So if you are in this region where phi is fluctuating a lot, and you're only focusing on the sigma, and the sigma is not fluctuating because K is large. So you want the flux to be the same on every point of the lattice, to be just 1 to minimize this energy. But imagine there's a point here where the flux is -1. This means that you have to flip the sign. So every one of these links has sigma ij equals -1. So this thing has flux pi. This is flux 0, this is flux 0. So only this plaquette costs energy. So you see that's again, that's the Wison, a flux of -1 in the Z2 gauge field. And this a particle, emergent particle in the spectrum. And it's not something any local operator can create. You can only create pairs of Wison. You will flip the sigma ij on a link. So there's a branch cut. There should be some other Wison somewhere else in the sample, at least if you, so it's not, so it's a fractionalized particle, just the M particle. And the phi particle, as it goes around, has to cross this branch cut, and hence there picks up a factor of -1 and a mutual semi. So everything I told you, you can also understand here, just by either doing a small j or a large j, or a small k or a large k expansion. You can see all of this, which is properties of the Z2 gauge theory. Okay, so that's, the phase diagram is sort of different, the axes are a little different, but you have the same basic 3 phases. What you also learn from, you can also say much more about the nature of these phase conditions. It's a bit more difficult from the other approach. This phase transition is exactly 3D icing. It's the dual of Wegener's condition. This is, of course, the old XY Wilson-Fisher transition. And this one is kind of like the square root of a Wilson-Fisher transition. Yeah, we'll talk about it. And really, I think there's still open questions of what happens here. Okay, any questions? All right, so now let me at least mention something that will, yes, Nadi.
So you focused on Z2, but I guess you could do the same thing for other groups, for example, Zn for larger n.
Yes.
So would you expect to find so many phases, one for each? And when n is big, there could be the phase diagram, even if you just did it as a Zn gauge theory, discussion, there would be lots of phases because Zn could be Higgs to Zm and so forth. It could be all sorts of phases.
Right.
So would you expect all of them to exist somewhere in the phase diagram of the original XY model?
Yes, yes. In principle, yeah. I mean, it's amazing how rich. Yeah, I mean, there's no proof because my mapping to the original XY model is a small k expansion, and it could be that some of those phases in a regime where the small k expansion doesn't work. But my guess is they do. Yeah, I think it should be all right. I mean, the question really it is an XY model almost by definition. The question is how rapidly do the interactions fall off and how non-local are they? All the phases present when every interaction falls off exponentially. I don't have a proof, but I would say probably. Yeah.
Will it be a highly frustrated XY model?
Absolutely. It'd be something that is not very natural from people studying XY models, but yeah.
I have a question.
Yes.
So I don't know how relevant it is, but in the toric code, in the usual quantum computing picture, we can introduce all these defects like twists, then introduce by introducing domain walls in the lattice, so that we can switch between E and M particles and things like that. How does that, or can we derive these things from this formalism?
I suspect so. I'm not such an expert on the twists you're referring to. It may be that some of those things are really interesting to quantum in the sense that they require operators that are not natural in the classical Euclidean formulation. Mm-hmm. But for the underlying boson model that I mentioned, for the superfluid state condition, I suspect there's some operation you can do on the boson model that will get all of those. Yes.
Okay. Thank you.
But, okay,
can I ask a question? The transition from long range order to fractionalization. Do we know it's the first order or second order, or
well, always be first order, but one possibility is what we call an XY star theory, or I think field theory has said it all before. So basically, it's a theory for phi, which is the XY order parameter, because you're going from phi not equal to 0 to phi equals 0 here. And so you can ignore the Y zones are gapped in both phases, so you can ignore them. But the reason the star is there is because if you put the thing on a torus, then you're allowed configurations in which phi goes to minus phi as you go around the torus. And local operators are always even powers of phi. So there's no local operator corresponding to phi itself. So in terms of the critical exponents, it's exactly the same. XY star and XY, all the exponents are the same, but certain operators are missing from the spectrum and certain new ones appear and so on. But so there's no more work to be done in terms of computing critical exponent. Those are all known. But you have to do some surgery on the spectrum of operators.
And can I also ask like a really general question?
Yeah.
So basically, I still have some problems of understanding what's going on in this fractionalization. So the very first and very basic question is, what does it mean for a particle or a configuration to have charge 1, for example, or charge 1/2? So what does it like?
Well, I mean, I would just go back to the original boson picture. All right. So, you know, if I take some configuration of bosons on a lattice, the Mott insulator, I have to be in the Mott insulator. If you're in the superfluid, then, you know, the global symmetry is broken and charge is not very well defined. But if you are in the Mott insulating phase, you can be either in the fractionalized phase or in the trivial phase. So in the Mott insulator, you know, you can imagine, well, if I could make a picture in terms of bosons, you know, the trivial phase is very simple. You have one boson on every site. That's my insulator. And now it's easy to talk about excitations that have charge plus or minus 1. Okay. And so if I add another particle, so I add a particle here, well, it will move around and maybe I can trap it in this region. But as it moves around, this whole region will have charge plus 1. Okay, and that's what it will have. And it's hard to see if this is my wave function, how this particle could split apart into 2. However, let's imagine that the wave function, it all depends on the ground state being highly non-trivial. Maybe this is not the correct description of the Mott insulator. You could imagine a description where the actual wave function is much more complicated. And what's happening is the following. Imagine that each boson doesn't sit on a site, but it rattles between 2 sites. Okay, so if I want to write down the ground state wave function, it's not just a simple product. So I have a boson which is rattling between these 2 sites. So this is equal to 1/√2 of a boson here and no boson there, and empty here and no boson there. Okay. So this particular state, if I count the boson number of this state is 1. This is 1 boson. So if I want to measure the expectation of the boson number operator on this side, it's 1/2, and on this side, it's 1/2. So now my ground state wave function, therefore, I want to write down a ground state wave function. On the average, it should have 1 boson on every site. And what that means is the ground state wave function will have 2 of these bonds on every site. So my, it's a complicated ground state wave function. I could have 2 of them like this, and so on. So there's some configuration. This is a configuration of dimers with 2 dimers on every site. And my wave function is this plus many, many, many other terms. So it's a highly complicated wave function. And now I claim that in this kind of wave function, I can create an excitation which locally has charge 1/2. And the way you do it, roughly speaking, is you just move this thing over by 1 step. So you have a little defect here where there's only 1 dimer coming rather than 2 dimers coming into it. And this little defect can move around and will have charge 1/2. So it's like a soliton where you suddenly move the rest of the dimers away. Okay,
so what you're saying then, if I take like the average over a finite region, then this average will give me back 1/2.
Correct. Yes. Yes. You may have to put some attractive potential so that it doesn't flow off to infinity. Some very slowly varying potential. You bring in some probe and you trap it. So you have some regions where you're trapping particles and you're just measuring the total density of particles. And you will find that sometimes there'll be half a particle in that region, exactly half. Yeah.
But there always has to be like the other half of the. So
Yes.
there has to be also a different particle.
Correct. Yeah. So that's why, and that's why this is not something you cannot create it on its own. It's an enyon. It's it's protected. There's no local operation that will change the particle number by half. But once you have it, it's protected, and that's in some ways the idea behind topologically protected quantum error correction. If you now put your qubit in the space of this protected space of half or not half, then that's protected to any local operation, to any noise. Yeah.
Okay. Yeah. Thanks a lot.
Could you say something? Could you say something more about? You said before about the phases that they are not described by Landau theory. Like, is there again an RG scheme describing these phases here, or is it something else for the topological phase?
Well, I mean, I wrote down the theory earlier. I mean, Landau theory for the U1 gauge theory is a pretty good starting point, but you do have to worry about non-perturbative effects of gauge fluctuations. So it's somewhat similar to what you do for the XY model in 2 dimensions. So the XY model in 2 dimensions, you do Landau theory, and then you find 2 phases. And then you look at fluctuations, perturbative fluctuations, and you find one phase has power law decay and the other phase is as exponential decay. So you say, okay, maybe there's still a phase. And then Costless and Fowler showed that when you put in the vortices the topological effects, then you get a complete story of what's going on. So if you do the same thing here, you follow the route of Costless-Thouless to this theory I'd written earlier of 2 scalar fields in a compact U1 gauge field, you will get the right answer. So what happened? And in fact, the monopoles are exactly the analog here of the vortices of the 2D XY model. The vortices of the 2D XY model in the high temperature phase form a Coulomb plasma. And here the monopoles in the high temperature phase, where H and phi are not condensed, form a Coulomb plasma. The difference is that in 3 dimensions, a Coulomb plasma is always in a plasma phase, whereas in 2 dimensions, the Coulomb plasma has both a confining and a deconfined phase. So when the plasma is in the plasma phase, means magnetic charges are free, then the electric charges are confined. So that's what Polakov showed. Almost simultaneously with Costless and Thouless, the arguments are very similar and they're just in different dimensions.
So is it again like an infinite order transition, right?
No. So the transitions are more complicated here. Yeah. So you don't have a KT transition anywhere in this. So that's more complicated. I'm just talking about the phases. These transitions. Yeah, so the C to A plus B is just the usual Wilson-Fisher. This is XY star. I just talked about that. And D to A plus B is just pure Ising, dual to Ising. Yeah, so the transitions are quite different. But the philosophy, the approach, the route that you would want to follow here is very close to the route you follow from the 2D XY model.
Thanks a lot.
Sure.
So,
one thing I want to say, which actually ties in naturally to this question. So this was for bosons and integer filling. And I got this rather strange looking state here. We have 2 dimers per side. So suppose I am talking about bosons at half integer filling or half integer spin. If you're talking about antiferromagnets, everything I've talked about today would apply to spin 1 antiferromagnet. Not spin a half. Now, certainly in the magnetic application, the half is the most important property. So what happens for spin a half? So let me just give you the answer, at least in terms of what theory we have to look at. And we're going to spend this next lecture deriving this and also studying some of its properties. So I've shown you this partition function here, d phi I over 2 pi. Some the sigma ij. And I'm going to leave a space here for the all-important term, exponential minus h. And h we learned was something very simple, minus j1 sigma ij cosine ii minus phi minus k product of brackets of sigma ij. So this is what we talked about. And in fact, this is, I believe, a very good description of bosons and integer filling with or antiferromagnets with an easy plane symmetry, with the U1 symmetry only, with integer spin. What about the half integer case, which is of course the most interesting case? Well, then unfortunately you cannot reduce it to classical XY model. You get another term, and I'm just going to write it over here. So we have power of 2s. So this is a phase factor, which can be either plus or minus 1. So it's nothing like classical, in classical stat mech, the weights in the partition function are all positive. And that was the case in everything we've talked about so far. All the weights were positive. Now we're going to get some negative weights. And what is this? Well, this thing is basically product of I, of the sigma I, on all the time links. So now it seems to be breaking relativistic invariance, but in the end it doesn't actually. So along the time link, so this is the time direction, and you have x and y in the other two directions, which I'm not showing. And you're periodic in time. So this is sigma I plus tau. Just take product all the sigmas and the time links. First of all, this is gauge invariant. If you have periodic boundary condition at time, it's what's called a Polyakov loop. Just the product of sigmas on all the time links. It's as if on every side of the lattice, you have a Z2 gauge charge just sitting there. And that picks up this Berry phase factor of -1. If S is half integer. And that's what you have to add. So this, so we'll talk about this and eventually derive it in some way. This is a much more complicated problem. And the phase diagram is different. Most importantly, the confining phase, the trivial phase is not trivial. And there are also some differences to the fractionalized phase, and so on. And this is actually much closer to the kind of problem that appear in condensed matter and quantum spin systems on certain lattices. And it's really the simplest environment where we can look at effect of these kind of background charge effects, if you wish. So the original RVB description that I talked about with the triangular lattice, I wanted to describe an RVB state of spin a half on the triangular lattice. I do have to include this term with the S equals 1/2 here. Okay, I'll stop here.
Okay, thank you very much for this very lecture. Do there are questions?
Okay,
one
everything
question.
I've said is in the notes, so please have a look at the notes. Yeah.
Yeah, sorry, one question. Will there be some parameter or area law behavior in the fractionalized phase?
Only in the limit. So let's just forget about this term here. Let's talk about here. If you take the limit J1 is 0, or basically, yeah, in that limit, the phi particles just disappear. And then the fractionalized phase is perimeter law, and the confining phase is area law. But the moment you put the phi particles in, well, the moment you put this term here, then everything is a perimeter law. But that doesn't mean that the phase transition disappears. The phase transition is still present because, for example, the Wisons are present here, but they're not present there. Or the half charges are here, they're not there. So there is still a distinction between the two phases, even though the Wilson loop criterion, the Wagner-Wilson loop criterion does not work. Yeah.
So even in that limit, does not reduce to a confinement, deconfinement phase transition?
No. So the universality class of the condition is the same. It's the Ising condition. The phase transition exists, it's present, it's the same universality class. It's just that the area law perimeter law diagnostic fails. It's not a good diagnostic the moment you have J1 non-zero. So that's why I didn't mention it. It's really not historically, of course, it's very important, but it's not, I think, ultimately the best way to think about this phase transition. I think the modern way is that, once you take the system, put it on a torus and look at the differences, and then there are very dramatic differences which are present whether J1 is finite or not. That's really how you distinguish the two phases.
And going back to a previous question, did I get this correctly? You mentioned that basically this field operator, which create with fractional charge, is always has always some non-locality. Is that correct, or was this specific?
It's always sorry.
Sorry.
It's always non-local. Yeah, I mean,
non-local.
It carries a gauge charge. It carries either U1 or Z2 gauge charge, depending on your formulation. And since every physical operator is gauge invariant, it's not something you can create by a local operation. Yes, it's always the case.